Now we consider another example, the Alice equation, y double prime minus xy equals 0. This is a valuable second order linear equation, and we will use the power series to find its solution. So we suppose the solution is of this form, is a power series. Then by direct computation, we obtain the second order derivative of y double prime. That is this is obtained from differentiating the power series of y term by term. Okay. Then the power of x in this expression is minus 2, so we will switch the index so that the power of x is the same as that of y. Therefore, so we let n minus 2 to be k, and then this is k from 0 to infinity, and then we replace k by n, so we get this expression for y double prime. And substituting all this into the equation, that is 0 equals to y double prime minus xy. That is this is the power series for y double prime. Then minus x xy, n from 0 to infinity, an xn. And now we will copy the expression for y double prime, and then we move the x inside the summation of the expression for y. That is the power of x increase 1 from n change to n plus 1. This is because x has been moved inside the summation. And to continue our computation, and there's no place here, so we need to go to the next page. So I copied the last line of this computation to the beginning of the next page. That is here. Now, how to deal with this? We will change the index of the second summation. Because the second summation, when n is 0, that the power of x is 1. But in the first summation, the power of x starts from 0. That is the constant term. So we write the constant term, that is n equal to 0, for the first summation separately. That is n equal to 0. Therefore, this is 2 multiplied 1, then a2. x0 is 1, so nothing. And plus n from 1 to infinity. That is n from 0 to infinity is split into n equal to 0 and n from 1 to infinity. Then we write the expression for the second summation, that is y, xy, sorry. But we also change the summation index from n plus 1 to n. The purpose of this is to for the later convenient to combine with the first summation here. So changing the summation n plus 1 to be n, then the n should decrease 1. So the range of such n is from 1 to infinity. As you can see, the first term in this summation is n equal to 1. The power of x is 1. And the index of the coefficient an minus 1 is a0. And in the previous step, this is also a0 and x. So these two summations are equal. Okay. So since these two summations here, the range of n and the power of x are all equal. So we can combine these two summations. Firstly, the first term we copy to this line, and then we combine the two summations to get the coefficient of xn is the xn is the coefficient of the first summation subtract the second summation. That is n plus 2, n plus 1, multiply an plus 2. This is the coefficient of the first summation, and subtract the second summation, the coefficient of the second summation for xn, that is an minus 1. And the left hand side of this computation, is 0. Okay, so it follows that 2a2 is 0, that is a2 is 0, and the coefficient of xn in the second summation should also be 0. Okay, so this is 0. For n greater than or equal to 1, this is 0. This is the coefficient in the summation of xn. So because a2 is 0, and using this relation of an plus 2 minus an minus 1, so we see that a2 equals a5, and for every a3k minus 1, the a are all zeros. Okay, because the jump from the index of these two, the coefficient of the two terms is 3. From n minus 1 jump to n plus 2. So we determine that a2, a5, and a3k minus 1. Okay, and for this is for n equal to 3k minus 1, and we also need to determine 3k minus 2, and sorry, this is let me see, 3k minus 2, n equal 3k minus 2, then here plus 2, that is 3k, and when n equal to 3k minus 1, here the n plus 2 is 3k plus 1. So we can use this relation, which the n here to be 3k minus 2 and 3k minus 1, to obtain a 3k and a 3k plus 1. Okay, you see, for this relation, recurrence relation, a n plus 2 and a n minus 1, when n is 3k minus 2, the a n plus 2 give us a 3k. Okay, and when n equal to 3k minus 1, the a n plus 2 is 3k plus 1. So we have a 3k minus 1, a 3k, and a 3k plus 1. All these three subsequence of a give us the complete sequence of the coefficient an. So in this line, we have already determined the sequence starting from a2. Now, using the m to be 3k minus 2 and 3k minus 1, we can obtain the other two sequence of the coefficient an. For example, a3k, that is when in this sequence, in this recurrence relation, we take n to be 3k minus 2. So we obtain the a3k is a3k minus 3. Here, this term, an minus 1, when n is 3k minus 2, this is a3k minus 3. So a3k is a3k minus 3 over 3k multiply 3k minus 1. Okay, so this is eventually to be a0, 2, 3, and 3k minus 1, 3k. Okay. Similarly, for n equal to 3k minus 1, we will obtain the a3k plus 1. a3k plus 1. So here, when n is 3k minus 1, the an minus 1 is 3k minus 2. So we obtain the relation from a3k plus 1, which the a3k minus 2. So this computing this turn by turn, and finally we will obtain the a1 over 3 multiply 4, and finally 3k plus 1. So this three sequence, the sequence starting with a2 are all 0. The sequence starting from a0 is given by this formula, and the sequence starting from a1 is this. Okay, so these three sequence give us the complete sequence of an, the coefficients. So our y is an xn, which is a0 k from 1 to infinity, 3k. This is the sequence for 3k. So A3k is 2, 3, and 3k minus 1, 3k. So this is the A3k here. Okay, we copy the A3k, which contain A0, and also we have the A3k plus 1. So that is related to A1, A1. And the A3k plus 2 or A3k minus 1 are all 0. So we only have these two power series. Okay. So here the 1, where is this 1? For this first series, this 1 comes from here. This formula is valid for k greater than or equal to 1, but the term A0 is 1. Okay, so the term when n equal to 0 is A0 that is 1 here. Similarly, the term containing A1, for the term containing A1, this sequence is also not applicable, because when you need to compute A1, then this k should be 0, but k could not k equal to 0 could not appear in the denominator. Therefore, A1 should be computed separately. Of course, the coefficient of the A1 correspondingly, this is x. Therefore, this is x. So our y is given by the linear combination of these two power series, which coefficients A0 and A1. So the first, the sum of the first series we denoted by y1, and the sum of the second we denoted by y2. So our y is the linear combination of this y1 and y2, and computing the Wronskian coefficient, Wronskian determinant, as we did for the previous example, y double prime plus y equal to 0, we will see that the Wronskian of this y1 and y2 at x equal to 0 is 1. So this implies that y1 and y2 are linearly independent. In other words, they form a fundamental set of solutions for our Alice equation. Okay. So this partial sum, the solution are presented by a power series. Of course, in practical computation, we could not compute infinitely many terms, so we can only compute finitely many terms. So this is the partial sum. Partial sum provides a local approximation for the solution in the neighborhood of the origin, because our equation is the power series is about x equal to 0. If the power series is about x equal to x0, then the x here should be x minus x0. But in our case, the power series is about the origin. That is x0 is 0. So our partial sum is a local approximation for the solution near 0. Okay, and of course, the approximation might not be very good. If you want a better approximation, you should increase the number of terms, okay, to achieve the required accuracy of the approximate solution. Okay, and moreover, from this power series expression for our y1 and y2, we can draw some conclusion about the y1 and y2. Although y1 and y2 are given by power series, not very easy to find the property of this solution y1 and the fundamental solution y1 and y2. But for example, differentiating y1 term by term, as a power series, we can differentiate term by term. Differentiating term by term, we see that y1 prime is equal to this power series. This is a new power series. So because the coefficients are positive, so we see that if x is non-negative, y1 prime x, the derivative of y1, is also non-negative, even strictly positive. This means that y1 is strictly increasing. Okay. Similarly, because the coefficient of y2 are also non-negative or even positive. So differentiating term by term, we also see that the derivative of y2 for positive x is also positive. So this means that y2 is also increasing, strictly increasing for positive x. Okay, so for x positive, these two fundamental solutions are strictly increasing. And for the case when x is negative, the power of x have some sign. So the derivative is no longer sign fixing. The sign will change. Therefore, the solution is oscillatory. But this it could not be seen analytically from the expression, from the power series expression for y, or even for the derivative of y. We could not find that the solutions are oscillatory analytically. But from the graph of the solution, this solution, we can discover this property of the solution. But analytically, we could not draw such a conclusion from the expression of y1, y2, and their derivatives. Okay.